Now we're going to apply perpendicular bisectors to triangles. When you have a triangle has 3 sides. So you're going to have a perpendicular bisector for every side of the triangle. Remember, there's 2 things that we look for when we're trying to identify whether or not something's a perpendicular bisector. We got to find our right angle box that tells us it's perpendicular, and we have to look for our tick marks that tells us it's the bisector. So RM, SM, and TM are all perpendicular bisectors, because if you notice, they have all right angles and the tick marks are there. So these perpendicular bisectors, RM, SM, and TM, are all concurrent. They all intersect at point M. So perpendicular bisectors, MS, and MT are concurrent. Because they intersect at one point. They intersect at point M. And this point of intersection of your perpendicular bisectors is called the circumcenter. So that's all one word. I just ran out of room. Circumcenter. The circumcenter of triangle NPQ. So the point where your 3 perpendicular bisectors is called the circumcenter. It's right here, nice and pretty. So point M is our circumcenter. The cool thing about the circumcenter is it's equidistant from the vertices. I can't fit this in that little blank. The vertices of the triangle. It's equidistant from each vertex. So if you look at this picture, if RM, SM, and TM are all perpendicular bisectors, we call this point M our circumcenter. And the distance from our circumcenter to vertex P is going to be the same as the distance from the circumcenter M to vertex N, which is going to be the same as the distance from circumcenter M to vertex Q. So your circumcenter is going to be equidistant to each vertex. So M and MP and MQ all are equal to each other. They all have the same length. Let's look at a triangle. So HG, JD, and KD are all perpendicular bisectors. So that makes point D our circumcenter. So D is the circumcenter. And we know that the circumcenter is equidistant to each vertex. So that means that from D to F is going to be 19. Oh, bless. That means that from D to F is going to be 19, from D to E is going to be 19, and from D to G is going to be 19. So when it says what's the length of DG, it's 19. What's the length of DE? It's 19. So from D to F is 19, from D to E is 19, and from D to G. So from the circumcenter to all 3 vertices, it's the same length. Okay, we know that if these bad boys are all perpendicular bisectors, so HD, DJ, and DK, those are all perpendicular bisectors. Remember, if it's a bisector, it has to slice that side, it has to cut that side into 2 congruent pieces. So EH should be congruent to HF if this is a perpendicular bisector. So if HF is perpendicular bisector, H is 16 of line. This segment perpendicular bisector JD, DJ is slicing FG into 2 congruent pieces. So FJ and JD are congruent. So if JG is 15, that means FJ is 15. The distance from this point, and then finally, to each DK is a perpendicular bisector. That means that DK, CD is bisecting segment AB, slicing that side. The distance from C to endpoint A is going to be the same. It's going to be congruent as the distance from your circumcenter is where your perpendicular bisectors intersect. So your circumcenter is equidistant to each vertex. This is the perpendicular bisector. Then any point on the perpendicular bisector is going to be equidistant to the end mean. So what that means is I could have also picked point E. Oh well, there we go. And point E, these perpendicular bisectors are the same distance. Mean to point are all cutting the sides. So really, you can pick any point on that perpendicular bisector. DJ cut side FG, and it'll be equidistant to the side EG in half. They're congruent. They're congruent. So if CD is the perpendicular bisector of that segment AB, then we can say that a segment AC is going to be congruent to segment CB. So the converse is true as well. If we have a point that is equidistant to the endpoints of a segment, so E, the distance from E to endpoint A is the same, it's congruent as the distance from E to endpoint B. Those 2 segments are congruent, those distances are equal. then that means that point E has to be on the perpendicular bisector of that segment. So if AE is congruent to EB, that means that this line, CE, is the perpendicular bisector. So it works both ways. Let's look at some examples. Okay, we're trying to find the length of segment AB. So I see my right angle box and I see my tick marks. So I got my two things taken care of. This means that line AC is the perpendicular bisector of segment BD. Line AC is making a right angle with segment BD and it's cutting it in half into two congruent pieces. So what that means is point A is equidistant from endpoint B and endpoint D. So that means that if AD is 4.1, that means that if AD is 4.1, then AB is also 4.1. Okay, this one is where we're going to use the converse. Point X is 9 units away from W, and it's 9 units away from Z. So point X is equidistant to the endpoints of that segment. So what that means is if this point is equidistant to the endpoints, that means that XY is the perpendicular bisector. And if XY is the perpendicular bisector, that means it's cutting WZ into two congruent pieces. That means that WY and YZ are congruent. So if YZ is 3, that means that WY is also 3. So WY is also 3. And then finally, okay, I see that Q, S, and ST are congruent. So I got the tick marks, and I have my right angle box. So it's perpendicular bisector. That means that R to Q is the same as from R to T. So I'm going to set those equal to each other. 2x plus 3 should be equal to 4x minus 7. I'm going to subtract 2x from both sides. I'm going to add 7 to both sides. And then I'm going to divide by 2. And x is 5. Then it asks me to find RT. So you got to read the problem. It says find RT. I got to plug that bad boy back in. 4 times 5 is 20. 20 minus 7 is 13. So RT is 13. And I can double check that by plugging 5 also into QR. 2 times 5 is 10. 10 plus 3 is 13. Check. So the big idea is if you see tick marks in a right angle box, that line is chopping that segment into two congruent pieces, making a right angle, that's a perpendicular bisector. And you can pick any point. So like if this is a perpendicular bisector, I can pick any point on that perpendicular bisector. I can pick one up here, and these distances are going to be the same. I can pick one up here, and these distances are going to be the same. Or I could pick one down here, and those distances are going to be the same. So you can pick any point along that perpendicular bisector, and it will be equidistant to the endpoints of that segment.